Hello there. In this video we're going to continue our discussion of improper integrals. That's the first type of improper integral. So type 1, improper integral, is ones of the form the integral from a to b of f of x dx, where a and or b are equal to plus or minus infinity, and f is finite on all of the interval ab. Now we're considering another type of integral. So type 2 will be of the form the integral from a to b of f of x dx, where a and b, or a and or b, are finite. F is finite on a, b, but f of a and or f of b is equal to plus or minus infinity. So let us look at the cases of type 2. So remember, for case 1, so type 1, we had the integral from minus infinity to a, we had the integral from a to infinity, and we also had the integral from minus infinity to infinity. So what we did was we took the limit as m goes to infinity of the integral from minus m to a. For the second, we did the limit as m goes to infinity of the integral from a to m. And for the third, we took the limit as m goes to infinity of minus m to m. And let's assume all these functions are integrable functions. So for type 2, we're going to do a similar approach. So what do I mean by the function is infinite at a particular value point? So, consider like y is equal to 1 over x on the interval 0 to 2. So 0 to 2 is going to be this interval. So it's finite on the interior, but it's infinite at the endpoint of 2. So case 1, let's assume that a is infinite. So let's assume f of a is equal to plus or minus infinity, and f of b is finite. So we're going to write the integral from a to b of f of x dx. We're going to define this integral to be equal to the integral from, so we're going to take the limit as epsilon goes to 0 of the integral of a plus epsilon to b of f of x dx. So that is, we're going to choose a point arbitrarily to the right of a. So that's case 1. So that's type A. Case B, let's assume f of a is finite, and let's assume f of b is infinite. So if that's the case, we're going to define the improper integral f of x dx. We're going to define this to be equal to the limit as epsilon goes to 0 of the integral from a to b minus epsilon of f of x dx. So here, now we have finite curve, but we have a vertical asymptote, say, at b. Right? So what we're going to choose is we're going to choose a definite integral on the interval a b minus epsilon, and then we're going to make epsilon arbitrarily close to 0 to see if it converges or not. And case C, let's assume that f of a and f of b are both infinite. So in terms of a graph, what would that look like? So that means we have a vertical asymptote here, vertical asymptote there, and we're considering the curve such as that. So, like secant or cosecant would be common functions. And we're interested in the integral under that curve between a and b. So what we're going to do is we're going to approach a from the right-hand side, and we're going to approach b from the left-hand side. So the improper integral ab of f of x dx will be defined to be equal to the limit as epsilon goes to 0 of a plus epsilon to b minus epsilon of f of x dx. And that is how we define our type 2 improper integrals. So let us do a couple examples to sort of illustrate how to figure out whether these integrals converge or diverge by these methods. And here it is important to define f is finite on the open interval ab. This is crucial. This will create the type 3, or the third type of improper integrals, which we'll discuss in the next video, which can be a little bit tricky, but we'll discuss it there. All right, so the first example, suppose we have the integral from 0 to 1 of 1 divided by x dx. So is this an improper integral or not? Well, notice that the function 1 over x has a vertical asymptote at the endpoint, right? Because we know that 1 divided by 0 plus epsilon is equal to something arbitrarily close to plus or minus infinity, right? So if that is the case, then that means this is an improper integral, and we need to use the definition of it. So this is going to be equal to the limit as epsilon goes to 0 of the integral from epsilon to 1 of 1 divided by x dx. Now, since epsilon lies in the region of continuity for 1 over x, we can apply the fundamental theorem of calculus, right? So 1 over x is continuous on the interval epsilon 1, where epsilon is a positive number. So that means we can use the fundamental theorem of calculus. Great. So that means this is going to be equal to the limit as epsilon goes to 0. So what is the antiderivative of 1 over x? So we know that that's the natural log of the absolute value of x. And we need to evaluate this as x goes to 1 and as x goes to epsilon. So as we evaluated at 1, we have the natural log of the absolute value of 1 minus the natural log of the absolute value of epsilon. All right, so the natural log of 1 is equal to 0. So it's the limit as epsilon goes to 0 of negative natural log of the absolute value of epsilon. So we can factor out that negative sign here. So we have negative limit as epsilon goes to 0. Now we can approach this from the left or the right. We should get the same exact thing. So let's just approach it from the right. So this is going to be the natural log of epsilon. So know that this, by the properties of the natural log of the function, goes to negative infinity as x gets close to 0. So we have minus infinity, if you accept this statement at least, is going to be some positive infinite quantity. So this integral diverges. So that means the integral from 0 to 1 of 1 over x dx diverges. That is, it does not equal to a finite quantity. All right, so let's do another example to sort of illustrate this. So example 2. So let's assume we have the integral from 0 to 1 of 1 divided by x times x minus 1 dx. All right, so what do we have here? So notice that if we have f of x is equal to 1x times x minus 1, the domain of f is equal to all real numbers except 0 and 1, right? Because those are infinite discontinuities of f. So that means both our endpoints are infinite discontinuities, which means we need to define this in terms of an improper integral. So that means this, by definition, is going to be equal to the limit as epsilon goes to 0. So we're going to approach 0 from the right, so that's going to be 0 plus epsilon. And we're going to approach 1 from the left, so that's going to be 1 minus epsilon of the function 1 divided by x times x minus 1 dx. So this is a continuous function on the interval epsilon to 1 minus epsilon, so we can use the fundamental theorem of calculus on this definite integral. So how are we going to treat this function? Well, we can use partial fraction decomposition, for example. So we can rewrite this as the limit as epsilon goes to 0 of the integral from epsilon to 1 minus epsilon of a divided by x plus b divided by x minus 1 dx. So we want these integrands to be equal to one another. So if that is the case, then that means 1 must be equal to a times x minus 1 plus b times x. So if we cross multiply on the integrand equivalence, then we get this relation. So if we let x be equal to 1, we're going to have that b is going to be equal to 1. And if x is equal to 0, we see that, okay, well that goes away. 0 minus 1 is negative 1, so negative a equals 1, so that means a must be equal to negative 1. So those are constants for partial fraction decomposition. So continuing on with our integral. So this is going to be equal to the limit as epsilon goes to 0 of the integral from epsilon to 1 minus epsilon. So a is negative, so I'm going to reverse these two. So I'm going to rewrite this as 1 divided by x minus 1 minus 1 divided by x dx. So I know the antiderivative of each of these functions, so I can distribute this integral over each of them. So I can rewrite this as the limit as epsilon goes to 0 of the function, the natural log of the absolute value of x minus 1 minus the natural log of the absolute value of x, evaluated as x goes to 1 minus epsilon and as x goes to epsilon subtracted. So that's the fundamental theorem of calculus. And remember, we can only use the fundamental theorem of calculus if this integrand is continuous. That is very important. All right, so let's algebraically deal with this. So we have two natural logs subtracted from each other. So let's make things a little bit nice. So we have the limit as epsilon goes to 0 of the natural log of the absolute value of x minus 1 divided by x. We still need to evaluate this at 1 minus epsilon and epsilon. But I'm going to simplify this just a tad bit. Actually, I'm not. I'm going to evaluate this. So this is going to be equal to the limit as epsilon goes to 0 of the natural log of the absolute value. So let's plug in 1 minus epsilon. So 1 minus epsilon minus 1 over 1 minus epsilon minus, so the lower limit goes in now, so epsilon minus 1 over epsilon. So we have two natural logs subtracted again, so we can divide their interior functions. So we can rewrite this as the limit of epsilon goes to 0 of the natural log, so super absolute value. So 1 minus epsilon minus 1, so 1s are going to cancel, so we have minus epsilon over 1 minus epsilon, all divided by epsilon minus 1 divided by epsilon. So we can cross multiply our fractions. So we have the limit as epsilon goes to 0 of the natural log of the absolute value of minus epsilon over 1 minus epsilon times epsilon divided by epsilon minus 1. So what do we have here? So we have this is equal to the limit as epsilon goes to 0 of the natural log. So we have negative epsilon squared on top. So 1 minus epsilon and epsilon minus 1 are just opposites. So I can rewrite that if I want to. I can rewrite that as epsilon minus 1 squared with a negative sign, indicate those positive numbers. So epsilon squared and epsilon minus 1 squared are both positive, so I can remove my absolute value bars. So it's just the natural log of epsilon over epsilon minus 1, the quantity squared. 2 is just a constant, so I can bring that out. So it's just 2 times the limit as epsilon goes to 0 of the natural log of epsilon divided by epsilon minus 1. So what do I have here? So this is technically still absolute value. So as epsilon goes to 0, this quotient goes to 0 and it's going to go to negative infinity, right? So if that is the case, then this definitely is not going to be finite. So this number is either equal to plus or minus infinity. You can decide which one it is. So therefore, the integral from 0 to 1 of 1 over x minus 1 dx diverges.